Okay, this is Unit 4, Day 4. Today's a little bit harder. So yesterday we talked about, well, what happens if you see a 2 out in front of the function? We just multiplied everything by 2, and that was a vertical stretch. And then we said, well, what happens if you see a 3/2 or a 1/2 on the outside? You would just multiply the function by 1/2, and then that would be a vertical compression. So your graph got wider, okay? So now what happens is you're going to notice things are moving inside the parentheses instead of outside. And if you remember, anything that went inside was opposite of what we thought. So, for example, looking up here, when it says -2, we would normally think that would mean 2 to the left, but we've learned on the first day here that it means 2 to the right. So now this looks like it would be times 2. We're going to do the opposite, which really means divide by 2. Okay, this looks like this would be times 1/2, opposite of, opposite of timesing something by 1/2, which is dividing by 2, would be multiplying by 2. So you're going to do the opposite operation here. Okay, find the coordinates of the vertex of F without the use of your calculator. So again, it's opposite sign, which would be +2, -3. Okay, using your calculator, sketch a graph of F on the axis, providing you're plotting with its turning points and zeros. Those are always the key functions there. Okay, so my F graph, my turning point I just said is at 2, and this graph is really hard to see, is at 2, -3. There's my turning point. And my zeros for my F are at 5 and -1. So I draw these in, and this is my F graph. Okay? So now, part C, consider the function g of x equals f in parentheses 2 times x. Determine a formula for g. Use your calculator graph and label it. All right, so it's opposite, okay? So you're just timesing it by 2. So wherever you see a x, which is up here, you're going to plug in a 2x. So it becomes g of x is equal to, now instead of writing x, you just write 2x minus 2. So in this spot, you substituted which was an x into as a 2x, and everything else stays the same, okay? So now I'm going to use my calculator. By using analyze graph, I find out that my turning point is at 1, -3, and my x-intercepts, my x, I can't write today, guys, sorry. My x-intercepts are at -1/2 and 2.5. So now I'll switch colors to keep this straight. So vertex is at 1, -3, but the x-intercepts is at -1/2 and 2.5. So as you guys can see, it's getting a little narrower, okay? The next part, now it's a 1/2x. So you're going to substitute in wherever you see an x in the f function. So up here where you see an x, you're going to put a 1/2x in its spot. So h of x is equal to 1/2x minus 2 minus 3. And again, use your calculator to find its turning points and its zeros. The turning point is at 4, -3. And my x-intercepts are at, oh, I found them. I didn't write them down. They are at -2 and 10. Okay, so let me switch another color here. I'm at 4, -3. 10 would be right here, kind of off my graph. So there's my h of x. And then my -2 is here. So you can see the blue graph, that's a bad line. The blue graph got wider, but the red graph got narrower. Okay, so now find the turning point for the F graph. We already had that. That was at 2, -3, so I'm just kind of collecting all the data here. F of 2x is part C. That was at 1, -3. And the turning point for my, when it was times a half, which is part D, is at 4, -3. What stayed constant about the turning points? If you guys look, the y values stayed constant. Okay, the y values did not change. They were all -3, -3, -3. So the y values stayed the same. What changed? What changed was the x values by the opposite operation. Okay, I ran out of room there. So for example, when it said f of 2x, you normally think that means times 2, but you're really dividing the x by 2. Okay, so here's the original, and when it looks like it's times 2, I really divided by 2, so 2 divided by 2 was 1. When it was f of 1/2 x, multiplying something by half is really dividing by 2, but in this case, you timesed it by 2. So when you start with this 2, you're going to multiply the x by 2. So your 2 times your 2 gave you your 4. Part G, how would you describe the visual difference between F and G and between F and H? Well, we already kind of talked about that. The G one gets narrower, so that's my red graph up top, and the H is my blue, and it gets wider. Okay. Example 7 or 18. Okay. So this one I forgot to read a little blurb. Example 17 shows a remarkable and counterintuitive concept about horizontal dilation. So the counterintuitive means opposite. So when it looked like it was times 2, we really divided by 2. When it looked like it was dividing by 2, we really multiplied by 2. Okay. So now it's talking about that, and make sure you guys know these. So when there was a number, a whole number, your K right here on the inside, that's a horizontal compression, okay? And compressions you normally think get wider. It actually got narrower. It's the opposite of the verticals, okay? And then when you think of that you're dividing something, it's actually a horizontal stretch, but it's getting wider, okay? So you kind of have to collect your thoughts and clear that. When it was vertical on the outside, it did what it did. Now this is completely the opposite, okay? So the next example here, consider the quadratic function, and it gives you, determine the coordinates of its turning point by using the equation. So x equals my opposite of b, which would be positive 12, times 2 times my a is 1, and that results in 6. Now when I go find f of 6, what does that mean? I'm really just plugging in 6 wherever I see x up here in the equation. I get negative 16. So my turning point is 6, negative 16. Part B. So now, ready? This is times 3. So you have to think you're really dividing by 3. So you're going to divide the x by 3. Okay? So what's going to happen is take this original point, 6, negative 16, and look at your x, which is 6. You're going to divide it by 3, and you're going to get 2, negative 16. Okay, and that is a horizontal compression. Okay, horizontal compression. So when it's a whole number, it's a compression. So it's opposite of when it's on the outside. Okay? All right, determine a formula for g of x and then find the coordinates of its turning point by using the equation for the x's of symmetry to verify your answer from part B. Okay, so basically, they're saying g of x, so they wrote this up in part B, g of x is equal to f of 3x. So go to your f function. Go to your f function, and wherever you see an x, you're going to plug in 3x. So it becomes 3x squared minus 12 times 3x plus 20. Okay, and then you're going to solve that algebraically, and you're going to get 9x squared minus 36x plus 20. Now using x equals negative b over 2a, find its turning point. So the opposite of b is 36 over 2 times 9, which is 18. You're going to get a 2. Okay, then take that 2 and plug it right back in here wherever you see an x. So 9 times 2 squared minus 36 times 2 plus 20, and you're getting negative 16. So this turning point is at 2, negative 16, which we already said we knew. So the only thing we did in part C is prove it algebraically. Part D, show that the y-intercept of both f of x and g of x are equal. Why does this make sense from a horizontal dilation perspective? All right, so y-intercept, you have to memorize this from the last unit. You know that's when x equals 0. So if I find f of 0, you go back to your f function, plug in zeros, you get 20. Okay? The g of 0, remember this is my g function right here in part C. I plug in a 0, I still get 20. So what is it proving? That the y's aren't changing, only your x's are. Example 19. We can truly investigate why this is happening by looking at a function that is only represented graphically. Okay, so you don't have to worry about this. So now in your head you need to say, I'm going to multiply the x's by 2. Okay, so again, there's only 4 definite points on this graph. So I'm going to write those 4 definite points on the side. So that's negative 3, 4, negative 1, negative 2, 3, negative 2, and 4, 3. So again, I just went through and wrote those coordinates down. Now I'm going to multiply my x's by 2, x values only. So it's going to be negative 6, 4, negative 2, negative 2, 6, negative 2, and 8, 3. Okay? So then I can go and plot those. And if you guys can see, only the x values are changing, not the y's. So this is opposite when those numbers were out on the outside. So remember, the one they gave us was f of x, and now this is g of x. All right. Evaluate each of the following by using the definition. So basically, g's definition. If you go back up top, they told us it's f of half of that x. So whatever they tell you g is, you take half of it in the f function. Okay? So what does that mean? I'm going to find f of negative 3. Now, how do I get negative 3? Because that negative 3 is half of what g is. So half of negative 6 is negative 3. So this one, it would be f of negative 1, because half of negative 2 is negative 1. This one would be f of 3, because half of 6 is 3. And then this one is half of 8 is 4. Okay? You could also just go up to your graph in the G graph. Now, if I highlighted the G graph for you guys in yellow, seeing that I didn't switch colors. So here's my G graph right here. Okay, that's my G graph. Okay. You could just go find its point. So what does that mean? That means at negative 6, you go over 1, 2, 3, 4, 5, negative 6. It's up there, and that's at positive 4. So 1, 2, 3, 4, 5, 6. You go up here at 4. But it's the same thing as going to the original black F graph at negative 3, and it's still up there at 4. Okay? And then same thing here. You're going to get negative 2, negative 2, 3. And if you guys notice, those are the points that we just found up here. Okay? So those go negative 2, and 3. This is just making you do it mathematical. All right, part B. Graph G, we already did that. How would you describe its graph compared to the graph of f of x? It's a horizontal stretch by 2. Okay?